So in this lesson, I want to do some example problems using the tangent line theorems. Here's our first question. From point P outside a circle, a tangent line is drawn to the circle. The point of contact of the tangent line is T. If the radius of the circle is 10 inches and the distance from P to T is 25 inches, how far is P from the center of the circle? Well, this is pretty useless without a diagram. We need a picture to start off with. So when we do these tangent line problems, it's very helpful to draw the tangent lines as horizontal with the circle sitting on top of it, like so, sort of like a wheel sitting on the ground. If you can, you should always try to draw or rotate your page so that the picture looks like this. It helps you visualize what's going on correctly. Now, let's add what we know. P to T is 25 inches and the radius is 10 inches. So there's 25 inches, and I've drawn the radius to the point of tangency. That's 10 inches. And we know that it will be perpendicular to the tangent line from the tangent radius theorem. This is the reason I like to draw the tangent lines horizontal with the circle sitting on top of it. It really helps to see where the right angle is in the problem, that it's here at the point of contact. Now, what's the question asked for? How far is P from the center of the circle? So that's P to the center of the circle. Let's add that segment in. Here we go. And this looks like we formed a right triangle. And our unknown is the hypotenuse of that right triangle. So we'll use the Pythagorean theorem. C squared, the hypotenuse, squared is 10 squared plus 25 squared. That's 100 plus 625, which gives me C squared is 725, taking the square root of both sides. C is the square root of 725. So the answer to our question, how far is P to the center of the circle, is the square root of 725 inches, or if we use a calculator, it's around 26.9 inches long. My second example. Concentric circles are circles with the same center. Suppose we have two concentric circles with radii of 4 and 10 centimeters. A chord of the larger circle is drawn that is tangent to the smaller circle. How long is this chord? So again, we need to make a picture. Here's our concentric circles. They have the same center. That's what it means for circles to be concentric, with the same center. That's the root of this word. Now, I haven't drawn any radii yet because I want to draw radii that help solve the problem. Too much stuff clutters. I don't want to just start drawing random radii in here to label 4 and 10. I want to draw a chord of the larger circle that's tangent to the smaller. So following the advice of the last problem, I'm going to draw my tangent line horizontal with this circle sitting on top of it. That's what I'm going to draw. I could draw other ways, but this really helps visualize what's going on. Now, I know the radius of the smaller circle is 4, and if I draw that radius to this point of contact, it will be perpendicular. So there's my right angle and my 4 centimeter radius. Next, when we're working with chords, if you remember, I like to draw the radius out to the chord always to the end point of the chord. I don't want to draw the 10 this way. That doesn't relate to the chord nicely. I always want to go from the center of the circle to the end point of the chord. So there's my 10 centimeter radius of the larger circle, and I formed a right triangle. So again, I'm going to be using the Pythagorean theorem. Let's label this unknown length B. It's not the hypotenuse, so I won't use C. And let's do the Pythagorean theorem. So I have 10 squared is 4 squared plus B squared. So 100 is 16 plus B squared. Subtracting 16 from both sides give me 84 is B squared. So B, this segment here, is a square root of 84 centimeters long. The chord is therefore twice that. 2 square root 84 centimeters, or looks like about 18.3 centimeters long. Here's my last example. We have a quadrilateral here circumscribed around a circle. What that means is that each side of the quadrilateral is tangent to the circle as it goes around. Circumscribed means drawn around. So there's my circumscribed quadrilateral. We're going to use the two tangent theorems to explain why the sum of the lengths of one pair of opposite sides of the quadrilateral is the same as the sum of the lengths of the opposite pair. So whatever this length is and this length is, if I add those together, it's going to be the same as these two. So what does the two tangents theorem say? It says the two tangent segments to a circle from the same point have the same length. So let's highlight a pair of these tangent segments just so you see what I'm talking about. Here I've done yellow right here. The two tangents theorem says these yellow segments have to be the same length because they're two tangent segments from the same exterior point. I don't know how long they are, but because they're the same length, I can use the same variable to represent their lengths. So I'm going to label each of these A right there. Now I can do the same thing walking around the circle with the other three pairs of tangent segments. In green, I've got B and B. In blue, I have C and C. Purple, D and D. Now, we're supposed to explain why the sum of lengths of opposite pairs of sides is equal. But look at the upper left, lower right pair. Upper left, lower right. This is D plus A, that side. This side is B plus C. So if I add those together, I get D plus A plus B plus C. The other pair are A plus B and D plus C. So if I add those together, I get A plus B plus D plus C. But of course, this here, D plus A plus B plus C, is the same as A plus B plus D plus C. So we're done. We wanted to explain why these two lengths here added together were the same as those two lengths.